the cloud. All right. Hello, everyone. My name is Roscoe, and we're here with Group 9. We have Peyton, Mirza, and Nazariah and Jamie with me today. This is our presentation on how virtual machines obtain IP addresses. So this is the executive summary. Our research project explores how virtual machines or VMs obtain IP addresses and establish network connections. So this process might actually sound simple initially, but it's actually very fundamental to how modern IT systems communicate, especially in cloud and enterprise environments. We started by looking at how hypervisors like VMware and Hyper-V assign IPs to virtual machines using methods like DHCP, static configuration, and MAC reservations. Then we compared the three main virtual networking modes, NAT, bridged, and host only, to see how they affect VM's connectivity and and visibility to the network. After that, we examined the technical layer in how virtual adapters and switches allow communication between virtual and physical systems. And finally, we analyzed how cloud providers such as AWS, Azure, and Google Cloud automate this same process at scale using dynamic IP management. Although this presentation shows how virtualization reshapes traditional networking, sorry, altogether, this presentation shows how virtualization reshapes traditional networking to make systems more flexible, scalable, and efficient. And so why does this matter? Understanding how VMs get their IP addresses matters because IP assignment is the foundation of network communication. Without it, virtual machines couldn't talk to each other, to the host, or to the internet. In the real world, this knowledge applies directly to cloud computing, cybersecurity, and IT operations in general. For example, if you work in DevOps or system administration, knowing how virtual IP management works helps you troubleshoot connectivity issues, secure virtual networks, and deploy scalable applications. It also ties into key concepts from this course, like DHCP, NAT, and subnetting, but in a virtualized context. So instead of managing physical routers and switches, administrators now manage virtual networks and cloud-based IP pools. That's why this topic isn't just theoretical, it connects to nearly every aspect of modern computing infrastructure.
All right, to get into it, hypervisors play crucial roles in virtualization by allowing multiple virtual machines to run on a single physical computer. It manages and allocates hardware resources such as CPU, memory, storage, and networking among the VMs, ensuring efficient performance and isolation. By creating and controlling virtual machines, the hypervisor provides a layer of abstraction between the physical hardware and the virtual environments. This allows different operating systems to run simultaneously on the same device. It also enhances security by isolating VMs so that problems or attacks in one do not affect the others. There are two main types of hypervisors: Type 1, bare metal, which runs directly on hardware and offers high performance and security, and Type 2, hosted, which runs on top of hosting operating system and is easier to set up. Overall, hypervisor is essential for enabling, managing, and securing virtualized computing environments. All right, so IP addressing methods. There are three that I will talk about today. The first one is manual addressing. This includes manual configuration. In manual configuration, the hypervisor host interface is assigned a static IP address, a subnet mask, and a default gateway. This approach gives administration complete control to who gets which IP address for how long, and this ensures every VM address is predictable. The second method involves dynamic host configuration protocol, which we talked about in class. DHCP is a network protocol that automatically assigns IP addresses, subnet mask, and default gateways to devices. The first being the DHCP process operates in four critical phases. The first being server discovery, where a client can listen in and search for available DHCP servers. During this process, the client is waiting for its call to be answered before proceeding. Next is the IP lease offer. During this process, the server connects to the client and sends out an available IP address that is local to the network. Then the IP lease request phase occurs where the client accepts and the address is sent out by the server. Lastly, the addressing process ends with IP lease acknowledgement, where the server confirms the assignment and stores that data. The third one is MAC addressing, known as Media Access Control reservations. A MAC address is a unique identifier that is assigned to every device that connects to a network, like a username for a device's network card. By using MAC address reservations, DHCP servers can be configured to assign the same IP address to the same MAC address every time that device enters the network. This ensures consistency by not requiring manual input each time. In virtual spaces, this method helps prevent IP conflicts by allowing administrators to easily track and manage IP assignments directly.
For NAT mode, the VM sits on its own private network, and the host basically translates its traffic. The VM can get out to the internet, but nothing can reach it directly. It's the safest and easiest setup because you don't really have to configure anything. This is usually what you'd use if you just need updates or want to browse from inside the VM without exposing it. Bridge mode is more like putting the VM on the real network. It gets an IP from the same DHCP server as everything else, so it acts like a normal device. It's great when you need the VM to be reachable, like for hosting something or testing how it behaves on a real LAN. The downside is it's more exposed, so you have to be careful with its security. Host-only mode completely isolates the VM. It can talk to the host and other VMs in the private space, but it can't get out to the internet or anything else. This is perfect for labs, testing, or anything else you want to keep contained. It gives you a safe environment without any of the outside traffic.
Each virtual machine connects to the network through a software-defined adapter that's managed entirely by the hypervisor. When a virtual machine boots, the hypervisor automatically creates and connects this adapter to one or more virtual networks. It also intercepts and routes the VM's network traffic through the virtual switches. This setup lets virtual machines behave just like physical computers while still keeping the isolation and flexibility between them. Virtual switches operate much more like managed Ethernet switches inside of the host. They forward traffic based on MAC address and can enforce network rules and policies. And then depending on how they're configured, a virtual switch might only connect internal virtual machines or bridge to a physical network interface card to allow external communication. In a bridge mode, the virtual switch passes packets directly to the host's physical network card, placing the virtual machine on the same layer 2 segment as the rest of the physical network. In NAT mode, the host performs address translation, so multiple virtual machines can share one external IP address while still maintaining private internal communication.
So as virtualization grew beyond just traditional on-prem setups, major public cloud providers such as Amazon Web Services, Microsoft Azure, and Google Cloud Platform had to transform how networks are built and how they're managed as well. So each of these platforms provides a software-defined virtual network. In AWS or Amazon Web Services, it's called a virtual private cloud. In Microsoft Azure, it's called the virtual network. And in Google Cloud, it's called the Virtual Private Cloud Network. So these networks or these environments create isolated subnets and routing domains, and this allows a user to have flexibility and security when they're using these cloud platforms. One of their key strengths is automated IP management. So, for example, when a virtual machine is launched, the platform's orchestration service automatically assigns an IP address and connects it to the appropriate subnet. So all that stuff is just automated behind the scenes. The actual user itself doesn't have to play around with that. It makes the entire process very smooth. And it also ensures fast, consistent, and reliable deployment. Again, without that manual configuration. In cloud networking, dynamic addressing is kind of what keeps everything running smoothly and efficiently. Rather than relying on static IP assignments, or local DHCP servers, the cloud server, the cloud software-defined control plane dynamically manages all the IP allocations. This means that when a virtual machine actually boots up, it automatically receives a unique IP address from the available pool, and then when it's shut down, that address is returned for reuse. This process again happens almost instantaneously and at scale, which is critical for environments that use auto scaling, load balancers, or container orchestration. Dynamic addressing also allows the network to grow and shrink, automatically, which then again provides consistent connectivity while reducing the need for manual network administration.
And so to conclude, how virtual machines obtain their IP addresses mirrors the evolution of networking from physical devices to virtualized and now cloud-based systems. Hypervisors manage IPs through manual settings, DHCP and MAC reservations, while NAT, bridged, and host-only modes determine each VM's visibility and access. In the cloud, this becomes fully automated through virtual private clouds, metadata services, and orchestration tools that assign IPs instantly and securely. The core idea remains the same. Every device needs a unique address to communicate. What's changed is the speed, security, and flexibility of managing those addresses. Understanding this process helps us design and secure the connected systems that run today's digital environments. Thank you so much.